Welcome to SS2 Physics, Term 1, Week 5. Today we study capacitors, devices that store electrical charge and energy. Capacitors are found in virtually every electronic device, radios, televisions, computers, camera flash units, and medical defibrillators. Understanding capacitance is essential for anyone who wants to work in electronics or electrical engineering. By the end of this lesson, you will define capacitance and solve problems using the formula Q equals CV, understand how capacitors behave in series and parallel, know the energy stored in a capacitor, and describe practical uses of capacitors. Let us begin. A capacitor is a device that stores electric charge. It consists of two conducting plates separated by an insulating material called a dielectric. When connected to a voltage source, positive charge accumulates on one plate and negative charge on the other. The capacitance C of a capacitor is defined as the ratio of the charge stored Q to the potential difference V across it. Formula: C equals Q divided by V. The unit of capacitance is the farad, F, named after Michael Faraday. 1 farad is an enormous capacitance. Most practical capacitors are measured in microfarads, μF, millionths of a farad, or picofarads, PF, trillionths of a farad. The capacitance of a parallel plate capacitor depends on the area of the plates. Larger area means more capacitance, the separation D between the plates, smaller gap means higher capacitance, and the dielectric material between the plates, characterized by its relative permittivity epsilon R. Formula: C equals epsilon naught times epsilon R times A divided by D, where epsilon naught is the permittivity of free space, 8.85 times 10 to the power negative 12 farads per meter. Example: a capacitor stores 0.006 coulombs of charge at 12 V. Capacitance C equals Q divided by V equals 0.006 divided by 12 equals 0.0005 F equals 500 microfarads. When capacitors are connected in series, the total capacitance decreases. Formula: 1 divided by C total equals 1 divided by C1 plus 1 divided by C2 plus 1 divided by C3. The charge stored is the same on each capacitor, but the voltage divides. When capacitors are connected in parallel, the total capacitance increases. Formula: C total equals C1 plus C2 plus C3. Each capacitor has the same voltage, but the total charge is the sum. Note: this is the opposite of resistors. Resistors in series sum directly, capacitors in parallel sum directly. The energy stored in a charged capacitor is given by W equals half times C times V squared, or equivalently W equals half times Q times V, or W equals Q squared divided by 2C. Example: a 100 microfarads capacitor is charged to 20 V. Energy stored equals half times 100 times 10 to the power negative 6 times 20 squared equals half times 100 times 10 to the power negative 6 times 400 equals 0.02 joules or 20 millijoules. This energy can be released very quickly. This is why camera flash units use capacitors. They charge slowly from a battery and then discharge in milliseconds to produce a bright flash. Capacitors have many important applications. In tuning circuits in radios, variable capacitors select specific radio frequencies. In smoothing circuits in power supplies, capacitors smooth out the pulsating DC from rectifiers. In timing circuits, capacitors charge and discharge at predictable rates to measure time intervals. In defibrillators, large capacitors store energy that delivers a controlled shock to restart a heart. In loudspeaker crossover networks, capacitors separate higher and low frequency signals. Summary of key points: capacitance C equals Q over V, measured in farads. Parallel plate capacitor, C equals epsilon naught epsilon R A over D, series, 1 over C total equals sum of reciprocals. Parallel, C total equals sum of values. Energy stored, W equals half CV squared. Capacitors store energy in the electric field between the plates. Contrast with resistors: resistors dissipate energy as heat, capacitors store and return energy. Remember, in series, capacitors behave like resistors in parallel. Reciprocal formula: in parallel, Capacitors behave like resistors in series, direct sum.